Okay, hi everyone. Thank you for joining GeoScience and GeoEnergy webinar of 4th of June 2020 today. These webinars are hosted by Sebastian Geiger at Heriot-Watt University and myself from TU Delft in the Netherlands. We are especially grateful to our keynote speakers who have supported this initiative and to you all to join us and combat work from home isolation. Please subscribe to our YouTube channel and help us spread the word. All previous lectures are available on our YouTube channel. Now to the lecture. It's our pleasure and honor to announce our keynote speaker of this week is Professor Philip Ringrose. Philip is adjunct professor in CO2 storage at the Norwegian University of Science and Technology, known as NTNU. He is also geoscience specialist at the Equinor Research Center in Trondheim in Norway. Philip holds BSc and PhD degrees in geology from universities of Edinburgh and Strathclyde, both in Scotland in the United Kingdom. He has published several articles on reservoir geoscience and flow in rock porous media, and also has co-authored a textbook on reservoir model design. He is chief editor of the journal Petroleum Geoscience and was elected president of the EAGE, European Association of Geoscientists and Engineers, between 2014 and 2015. In 2018, he was appointed as honorary professor on sustainable geoenergy at the University of Edinburgh School of Geosciences in Scotland. His groundbreaking work, especially on various geoscientific aspects of CCS projects, is known to the geoscience community. Still, I would like to mention perhaps to our student audience of our webinar that his Google Scholar page lists most of his publications. Please do pay it a visit. It's our pleasure and honor to host him. Please note, Philip's lecture will last for about 30 minutes, followed by questions and discussions. Like before, please type in your questions in the chat room, and Sebastian will chair the discussion session after Philip's lecture. Philip, thank you once more. The stage is yours.
Thank you, Hadi. You were too nice in the introduction. But it's a pleasure to be part of this series, and I've really enjoyed it so far. So I hope I can add my bit to a good series. And I guess you'll let me know if there's anything technically not working with the audio or the video, but seems to be okay. So what I'm going to do today is talk about designing CO2 storage projects and then into the strategy for scale-up. I have a dual position at the University of NTNU, and I also work at the research center in Equinor, and I'll use a lot of Equinor operations, but all of the data I show is from published work, so you can access it if you want to. So what I thought I'd do is I'll tell you a little bit about what I see as the key issues for CO2 storage projects. I'm going to go quite quickly through phase behavior, plume monitoring, pressure management, dynamics of CO2, and geological surprises. I am a geologist, so the geological surprises are always what interests me. But I do appreciate that I need to understand the physics of this process. And I've really enjoyed some of the more fundamental lectures you've had in this series, understanding flow in porous media, how multi-phase flow actually works in terms of wetting behavior, capillary forces, and the like. So I am going to talk a little bit about going from physics, which takes you a long way, but also into the engineering. How do you combine that understanding of fundamental physics into geophysics and into engineering? And after that kind of introduction to CO2 storage projects, I'm going to start thinking about the future. How could we perceive this experience being turned into a significant activity to mitigate climate change? So here's a very simple sketch of what a CO2 storage project looks like. The CO2 has got to be transported in some way to a wellhead. It could be a ship or a pipeline. This is a marine system, but it could also be onshore. And what I've sketched in here is you'll need to know the wellhead pressure, the bottom hole pressure, and some kind of time function for pressure evolution into the reservoir, as well as a space function for how the pressure evolves with distance from the well to eventually reach the native reservoir pressure. And then another key issue is where the CO2 plume will go, how it will fill the structure, and will it, for example, spill out of the structure. So that's the very simple concept. And I'm going to go through some of the learnings that projects have seen about how this behavior occurs in reality. And I have to do a little book plug, but my NTNU course notes are now written up as a little book. I emphasize it's a short textbook, but in there you'll find more details of the projects I'm going to describe along with the references. But I also emphasize that everything I show you, you can access pretty much through open access papers. The Snøhvit project, which I'm going to start off with first, it started in 2008. It was very pioneering in the sense that it was the first project to connect an onshore capture plant, which was integrated with a large liquefied natural gas processing facility, and connect that via 150-kilometer seabed pipeline to an offshore development, which was also subsea. Obviously, the CO2 capture and storage was integrated into a gas field, so to some extent, the gas facilities were used to as a framework for the CO2 storage. But it was pioneering in the sense that we demonstrated in this project how the functioning in terms of pressure dimensions for this kind of project was. The injection was at 2.5 kilometers depth, and I'll spend most of the time about the subsurface aspects, but I don't want to skip the facilities aspects. The design for this project involved an 8-inch pipeline. It was the first offshore marine CO2 pipeline, although there are many onshore CO2 pipelines in, for example, the United States. And there was a number of studies to try and understand the thermal behavior and the safety behavior of pipelines. And in the picture here, you see a heat transfer rig to try and understand the thermal coupling between the native environment and the pressurized CO2 in the pipeline from a paper published by De Koya in 2009. And I'm not going to talk much about facilities, but just remind you that there's plenty of work on engineering design of the pipelines. The latest project in Norway, which is very much in the public domain right now, it's called, well, the storage part is called the Northern Lights project, and it's part of the Norwegian full-scale CCS project. The storage part is a partnership between Equinor, Shell, and Total, and it's a strongly state-driven project with a lot of funding from the Norwegian state. And we expect an investment decision from the Norwegian government later this year. And there's certainly in Norway a lot of hope that this project will go ahead and be one of the pioneers in moving CCS forward. And in the sketch on the left, you see the basic design is that ships will take the CO2 from the Oslo area where the capture points are, and the ships will go around the coast, and they will end up at a sort of coastal terminal, which will have temporary storage or tanks, and from those, the CO2 will be pressurized into a pipeline and injected subsea. And you can see how that part of the storage project is very like Snøhvit, and we use very many of the learnings from the Snøhvit project to dimension this new project. The shipping concept is to have one ship per capture site with a capacity of about 7,000 meters cubed CO2 per ship. And the pipeline design here is 12-inch, slightly larger than the Snøhvit pipeline, allowing some capability for future scale-up. So that you can also find about online, and I put the website there if you'd like to check it out. So on to some of the issues. The first one is the phase diagram. If you work in CCS, you do need to understand this diagram. You and I breathe out CO2 as a gaseous phase every breath. So we're used to CO2 as a gas, but when we compress it into the subsurface, it turns into a liquid. So this diagram, this version of the phase diagram, just explains those paths. And I find that a lot of people working with CCS still find it hard to get their mind around the fact that we're dealing with a liquid in the subsurface. And it's not a liquid we're very familiar with. It has gas-like viscosity and fluid-like density. So let's just take through these cases. So I talked about Snøhvit at the beginning. We start with 1 atmosphere CO2. We're going to compress it. And in the Snøhvit project, we compress well into the liquid phase at the wellhead. And then as it gets to the bottom hole pressure, the temperature increases. And to some extent, the pressure increases further. And then because we're injecting at 2.5 kilometers depth, the reservoir is very hot. So the CO2 further warms up into the reservoir. So this ellipse is showing you the range of temperature and pressure into the reservoir domain. So there's a heating of the CO2 into the reservoir. But we're always within the liquid or dense phase. In the Sleipner project, which is slightly shallower, the compression takes the wellhead pressure to very close to the critical point for CO2, about 65 bars pressure at the wellhead. And then as we get down to bottom hole conditions, we're pressurizing and warming up as we would expect from thermodynamics. But then the CO2 will cool into the formation. And it actually cools as it rises through the formation to very close to the critical point. And there has been in the Sleipner project some discussion about whether we've actually entered the gas phase in the storage domain, but we still are pretty sure that we've stayed within the dense phase in the storage domain, but we're very close to the critical point. And it means that the density changes are quite significant for the Sleipner project because we're so close to that critical point. And one of the first learnings in storage project design is that thermal gradients can be very important and can mean significant changes in density. And that has implications for how you approach modeling of CO2 in the subsurface. And then the other thing is that we need to think about minor components in the CO2 stream, because the phase diagram I've shown you here is for pure CO2. But if you add minor components of methane or nitrogen or whatever, you will change that diagram to some extent. For example, adding 5% methane will shift the critical point by about 3 degrees centigrade. Another key feature of project design is that we try and keep the aqueous phase to a minimum, because adding water into the CO2 injection stream will significantly increase its corrosive behavior. So most projects try and keep the aqueous phase down to ppm level. 50, 100 ppm would be the typical numbers we're talking about. So that's a little bit on the phase diagram. And then if I move on to the well itself, the Sleipner project, which has been the longest running, a single horizontal injector has provided fairly stable injection for 23 years. The well is built with fairly standard well design, except that it has quite a lot of high chromium steel components. So all of the exposed members, like the injection liner and the injection tubing, have high chromium steel specs. 25% chromium steel is a very expensive steel, but it ensures you have very good resistance to corrosion, whereas some of the other elements, like the casing, can be a lower specification of duplex steel. So one of the learnings is you can use a standard well, but you have to think a little bit hard about the well materials you're going to use. Now, because Sleipner has been such a long-running success in terms of injection, we've injected over 18 million tons now in this single project. A lot of people think it was a piece of cake. Well, if you look into the project, it wasn't a piece of cake. In the first year, the project had a lot of challenges with the well operations. They had sand influx into the horizontal well, and they had a significantly reduced injectivity due to sand collapse and plugging of the completion interval. So what the project did way back in 1996-97 was do a full workover and install sand packs and gravel packs over a shorter interval, which ended up being 38 meters long, to achieve a much better injectivity, which is what has followed for the remaining 17 years, 22 years. And I've just shown you some of the injectivity numbers in here. In the design phase, the project expected to have an injectivity of about 2,000 cubic meters per day per bar. When they started up, they had a tenfold drop in that, so 200 meters cubed per day per bar, which was way too little to achieve the goals of the project. But after the workover, things returned to a much better injectivity, and in fact, the injectivity has been better than expected. So it just shows you that no project is a piece of cake. You have to go through the problems and solve them one by one. But following those initial challenges, the project has actually gone extremely well and stably. Here's a couple of geological graphs or images of the Sleipner site. We're injecting into a fairly homogeneous sandstone with very high porosity and net to gross over Darcy permeability, and generally pretty homogeneous with some thin shale streakers. In the image to the right, you see the two-way travel time map at the top Utsira level with two structural closures that are indicated with the injection point shown here. And when the project started out 23 years ago, there was no specific knowledge about how this would go. There was just the intention that the project would gradually fill the geological structure that we see there. And one of the other great learnings from the Sleipner project has been the valuable insights gained by time-lapse seismic imaging. And this very nice 3D graphic created by Anders Schär as part of his PhD at NTNU shows you a 3D reconstruction of that plume detected by time-lapse seismic. And what we see there is that it's a complex plume. It has 9 layers, and each layer has a different geometry. And the top layer is the one that's filling the top structure image that I showed you just back there. And I don't think anyone would agree we fully understand what's happening at Sleipner. A lot of research institutes around the world have studied this data set. But overall, we use that time-lapse seismic imaging to show that the CO2 is roughly where we expect it to be, and to confirm that it is contained within the structure. So there's positive insights. And to also demonstrate how useful time-lapse seismic monitoring is in a CCS project. But then also to learn from that, as I'll show you in some subsequent slides. There was a nice review paper by Anna Karifuru and colleagues on the monitoring program, because a lot of people wanted to learn from Sleipner to say, well, what would you do in the next project? The Sleipner project so far has collected 9 repeat surveys, shown by this image in here, against a baseline, which you might think was perhaps a little bit over the top, and they're quite expensive surveys. So one of the questions we're asking now is, how many surveys do you really need? But because this was a pioneering project with a lot of research funding in the early days, it was felt that early focus was justified. We also collected 3 repeat gravity surveys, and we've done various visual monitoring surveys with other research institutes involved, as well as looking at the sea bottom. And the story of monitoring at Sleipner has very much been learning as we go to try and find out what is useful. And we're turning a lot of that experience into future recommendations for future projects. In terms of monitoring, the 2 big questions are conformance and containment. Can you demonstrate conformance, which is that the project is going according to plan? And can you demonstrate containment, i.e. the CO2 is not leaking? And another interesting thing happened in Norway in 2014 and 15 is that the new legislation for CO2 storage was implemented into Norwegian law based on the European directive. So the site was re-permitted in 2015, and it now is compliant with the new directive. But very much Sleipner was informing the law as well as responding to the law. So it's very much a demonstration project about what is useful. I'm going to move quickly on to the Snøhvit project. And of course, in the Snøhvit project, we were learning also from Sleipner. So we also collected time-lapse seismic data for Snøhvit. But by the time Snøhvit came along, we had a downhole gauge in the well, so we were able to monitor pressure much more accurately. And we had another set of problems at Snøhvit. We had other injectivity challenges due to a salt dropout near the well, and they are, if you like, witnessed by this fluctuating pressure gauge at the beginning of the injection. And then in the first few years of injection, there was a steady rise in the bottom hole pressure, which, if it had been allowed to continue, would eventually have exceeded the fracture pressure, which was obviously not permissible. So then a workover was engaged in that project, and a new injection plan was put in using a modified completion. And since then, the injection has gone very well with a stable pressure. So that's the kind of monitoring story, that we used a combination of time-lapse seismic and downhole gauge data to understand what was happening. And the story was basically most of the CO2 was going into the lowest layer and very little was going into the upper layers. But there's a geological aspect to the story as well, is that we were injecting into a fluvio-deltaic reservoir with some geological barriers. When we switched the injection plan to inject into a shallower formation, we were injecting into a shallow marine geological unit, which had fewer lateral barriers. So we also learned quite a lot about how geology interacts with an injection plan. But probably the most important learning from Snøhvit is the need for some flexibility on your well design, the ability to change your injection plan as the project proceeds. This image shows you the same thing in cross-section. The red dots are the lower completions that we started with and had, experienced pressure limits in that zone, and the upper red rectangle is the new completion in the Stowe formation, which we've used since. So what we did was we changed the location of the injection to get an acceptable pressure response for the injection required. And so far we've injected 6.5 million tons in this project, with 1 million tons in the lower unit. And then thinking on the plane view, so if I just switch back again, what the next image is going to show you is a geological and seismic map of this unit, the Tuborn down here, which I explained was a fluvio-deltaic system. So here's a map of that unit that we were injecting into. The red dot is the injection well point, and the colored tones are the acoustic impedance map from seismic, which has been color-coded according to, if you like, reservoir quality or porosity. And then the lines are a geologist's sketch of what they think we're seeing in here. We know we're in a fluvial delta, which is these channelized systems in yellow. And we think that the region we're injecting into has a series of mouth bars at the front end of a deltaic unit. And after the experience of injection, we were able to infer that probably we were injecting into a good sand here, but then we were encountering some barriers quite close to the injection point, which limited the pressure growth. And in fact, the pressure barriers in this well, which we could infer from inverting the well test data or the well gauge data, showed us we probably had a mix of sedimentary barriers and structural barriers, because there are also faults in the system. So we learned a lot, and if I was to summarize the question of geological surprises here, is that in all the CO2 projects I've been involved in, what we found is that there were always some unpredictable geological factors that we only discovered about during injection. Nobody can predict everything in the subsurface. And as you start injection and monitoring the injection, you will start to find out which factors, which shales or which channels or which faults might be most important in controlling your reservoir. And that kind of leads to an implication for CO2 storage projects in the future. You're always going to have to proceed with limited subsurface data. Therefore, you need to understand geology, you need good concepts, but you also have to have an adaptive approach to plume management, which means having monitoring data, and it means being able to change your well completion plan if necessary. And that's certainly one of the key lessons that we've learned over the years about CO2 storage projects. Switching back to Sleipner, here I show some examples published by Williams and Chadwick in modeling the Sleipner plume. And they show similar things, that the bar sandstones, channels and bars at the top of the Utsira, shown by these isochore maps here on the left, had a significant control on the plume development. And on the right, or the orange pictures in here, you see their model match to seismic. The black outline is this time-lapse seismic image, and the orange tones are the model predictions. And the predictions are very good. And what Williams and Chadwick showed in this paper is that it's a combination of permeability, heterogeneity, and the thermal effects that dictate how good you are at matching this plume. So, you know, and numerous groups around the world have looked at the Sleipner case, which is good. And in a way, partly to try and provoke and channel that enthusiasm in the research community, earlier this year, via the CO2 data share portal, which is online for all of you to look at, we've shared an updated Sleipner benchmark model, which is as good an information we have about the storage domain, and it allows users to try and understand CO2 storage and model it and test different assumptions. And the point about this data share portal is to make available well curated and documented data sets for researchers to try and, you know, spread the learning from these projects globally. So have a look there if you're interested. So let me summarize up what we've learned a little bit from CO2 storage and this link from physics to engineering. You know, the theoretical flow and porous media have really given us a good basis to understand how CO2 plumes work. We know about mobility, buoyancy, residual trapping, dissolution in brine, and mineralization. So those are the physical processes that operate. In the sketch here, I've shown you roughly how we think CO2 plumes behave. There may well be some residual CO2 behind a migrating plume. And as the plume migrates up dip, it will tend to form fill structural closures and thin out. And there may well be some, well, there will be some dissolution in the brine driven by convective mixing and diffusion processes. So the physics is understood, but the value of the real projects and the monitoring data is that we then start calibrating the physical models. And here is another example from Snøhvit, the shallower injection interval, where I compare the time-lapse seismic data in cross-section with a high-resolution reservoir simulation model, just to show you that there's always going to be a scale difference, but we can use time-lapse seismic to calibrate and refine our models. And we're doing that continuously. And I think we can expect to see, you know, continuous improvement in our ability to forecast CO2 plumes based on these well-characterized sites with good data. So I want to finish up the first section with a little, you know, look back to the physics. Fundamentally, the physics of CO2 injection is well understood. If you inject a low viscous fluid into a higher viscous medium, CO2 displacing brine, we know that that's an unstable mobility ratio, and the mobility ratio is probably between 5 and 20 in the subsurface, depending on the temperature mainly. And this is a nice a redraw of a nice paper by Ockwin and others, which looked at the effects of mobility and gravity viscous ratio. So from the viscosity point of view, we would expect the efficiency of CO2 injection to be between 5 and 20%, say, depending on the mobility ratio. That's on this axis here. But as you introduce the gravity group here, you start to reduce that efficiency. And we think that when you take into account all the forces, the domain for typical storage field conditions means that you generally have an efficiency of less than 6% in terms of total pore occupancy in the storage domain. And that may surprise you that it's quite a low number, but that's what the physics tells you. And in fact, we can use the very good time-lapse seismic imaging at Sleipner to pin down that number for a real case. And after 20 years at Sleipner, we think our efficiency is about 5%, which very much matches the theory. And basically what's happening is that as you introduce CO2 into a reservoir unit, it will tend to rise as an inverted cone with that viscous dominated plume shape, but gravity segregation effects will further encourage the CO2 to fill mini structural traps within the system. And that process makes CO2 storage not super efficient. But obviously, if you understand the geology, then geology can make the storage more effective than just going into a homogeneous medium. And then switching back to the geophysics, here's a sort of higher resolution image of an example time-lapse amplitude difference map or section for the Sleipner case, differencing the 2010 seismic survey with the baseline in 1994. And we can use that time-lapse seismic imaging to image the multi-layer plume. And that's the data that I've used to try and estimate the overall storage efficiency. So roughly speaking, you can say it confirms theory, but then it shows how these multiple layers with thin shales have actually controlled the real storage efficiency. And we continue to use that seismic data to try and build confidence and knowledge about how storage operates. So let's summarize that and say, well, okay, so what have we learned from all these projects? First of all, injection rates between 0.3 and 0.9 million tons per year so far. I've tried to explain to you that injectivity and capacity are highly dependent on reservoir properties that you learn about during operation, and that geological heterogeneity means we'll need some flexible well solutions. I've talked a little bit about pressure and fluid management and the importance of reservoir monitoring. So, to wrap it up, it's about injection well management and geophysical monitoring as the top topics in my personal view. I'm sure there'll be others that would like to mention other things. And so for the last 5 minutes or 10 minutes, if I'm given that time, gentlemen and ladies, is I want to just think about the future. If we took that experience and made a map to the future, what would that future look like? Currently, there are 19 large-scale CCS projects in operation globally. Most of them are using EOR for the storage, but an increasing number are focusing on saline aquifers. And then the question is, well, is this ever going to reach a climate significant level of activity? Because at the moment, it's certainly not significant enough to be to have a global impact on climate change. So I want to talk about the most recent study I've been involved in, which is work I did together with Tip Meckel at the University of Texas, where we took a global look at this problem, and we looked at all of the offshore basins, and we've particularly focused on offshore storage for geological and political reasons. And we've tried to develop a geo-pressure approach or basin approach to this problem. And what's interesting about the world we live in is that the continental margins have massive, massive thicknesses of sediment. The color codes are based on gravity inversion data, showing you that we have between 2 and 5 kilometer thickness of sediments around most of our continental margins. And it's also interesting that we human beings, we mostly live along the coastline, and we mostly live where the rivers meet the coast, to put it very simply. So these offshore sedimentary packages are actually very well located for us to dispose of CO2 captured by our, industrial clusters. On this map, you also see the oil fields, which are also, occurring in those same sedimentary basins. So what we wanted to do in this paper is to say, well, how can we learn from basin history from the petroleum world and turn it into a picture for the future? And what we concluded, and I'll come to the conclusion first, is that we are going to need as a global society 12,000 injection wells by 2050 to achieve the 2-degree scenario for global warming in the Paris Agreement. How do we do that? First of all, we reviewed the basin data in the Norwegian offshore and the Gulf of Mexico. And we looked at the characteristic fluid pressure and lithology overburden pressure gradients, as well as the fracture pressure, which is determined by especially the minimum stress field vector. And we showed that, at a first approximation, Gulf of Mexico and the North Sea Basin have very similar characteristics. Both of them tend to have normal hydrostatic pressure down to about 3 kilometers, and then you get into a zone between 3 and 5 kilometers where you have significant overpressure. So that's our starting point, understand the basin. And then we took that basin profile and we said, okay, where is our storage domain? We know that many nations have mapped the potential storage, and for example, 160 gigatons of storage have been mapped in the North Sea Basin. United States or the North American storage resources over 2,000 gigatons. But the question often is, well, how would we exploit that resource? And will there be pressure limits to doing it? And what I'm trying to point out here is that when we've been developing oil fields over the last 100 years, we've often been relying on natural buoyancy pressure of the oil field, which has a natural overpressure. When we think about CO2 storage, we're generally going to want to go from the initial hydrostatic pressure up towards, but not beyond, the fracture pressure. And that domain for repressurization is actually enormous globally. And there are also cases of gas fields that have been depressured below the hydrostatic pressure, which create another kind of pathway, which we call depressurization pathways. But I'm just going to focus on the case of going from hydrostatic pressure upwards. And to address this problem, we said, okay, let's create a generic plot for pressure for a typical CO2 storage project. We know we never want to exceed the fracture pressure, so we're going to have a bottom hole well pressure which must be below that. And we're going to have an initial pressure which will probably be close to hydrostatic. And as we inject CO2, there will be a tendency for the pressure to rise towards some final pressure. And if you think about it that way, you can imagine that there's two types of storage target. Storage geometry A are storage targets where you are able to fill the structure before you reach the limiting pressure. And storage geometry B are where some kind of pressure barrier hinders you from filling the whole structure. So geometry B's are pressure limited, whereas geometry A's are not pressure limited. And then to turn the pressure story into a volume per well story, we just integrated the injectivity equation over the lifetime of the project. So you know the P initial and the P final, and then you can use characteristic pressure functions from well test type inversion to work out your expected volume stored with that pressure context. And then the other thing we needed was to know roughly how much CO2 we deliver per well. So we collected all the empirical data that is available from the many projects around the world, including Sleipner, but also projects in Canada, USA, etc. And we created statistics for delivery of CO2 per well. And our P50 for the offshore case was about 0.7 million tons. P10, the maximum was just over 1. And this is an empirically based data set, so you could certainly optimize that into the future, but it gives us a reasonable basis for prediction. And then we tried to capture different scenarios for the pressure evolution for different levels within that system. And I just show you here some of those scenarios. You might have shallow aquifers with very limited pressure constraints, or deep aquifers with very significant confined barrier systems where your pressure would rapidly rise towards the limit. And we tried to capture a range of this behavior in our concept. So I'm coming to the end of my time, so I'll just show you the conclusion we came to. What my colleague Tip Meckel did was pull out all the databases for historic well rates for 3 basins: Texas offshore, the Gulf of Mexico in red, and the Norwegian case in the sort of greenish color here. So if I just take you through this plot briefly, we've got the number of wells on the left axis and the cumulative CO2 injected on the right axis. And the transform between wells and CO2 is based on the data I just showed you in the previous slide. If you look at the history of Texas, when they discovered oil, they started drilling 10 wells in the first decade. Then they got excited and they went up to over 100 wells. And then the basin matured to over 1,000 wells. So each petroleum province had a kind of maturation history. And here's the maturation history for the Norwegian continental shelf, and here's the one for the whole of the Gulf of Mexico. And then what we did is we said, well, let's imagine the same activity happens in the future in terms of drilling activity. And so we start that drilling activity in 2020, and then we see how many wells does it take to deliver the volumes needed for the Paris Agreement. And our storage target is based on the IEA projection for global CCS deployment, which is expected to be about 7 gigatons per annum by 2050. So that's the green line at the top. And our conclusion was 12,000 wells would do the job. And if I break that down, you can look at it as one Gulf of Mexico would probably do the job globally, or if you take the Norwegian case in the middle here, 5 Norwegian projects would do the job globally. Now, these are only meant as an analogy, so let's think about how it would work in practice. So let's imagine that each continent has a cluster for CCS, okay? And let's imagine that each cluster is modeled on the Norwegian well rate, okay? Then we can ask, well, how many wells will each cluster need to deliver the storage required? And splitting it into 5 global clusters, in the next 10 years, each cluster is going to need about 200 wells. And by 2040, each cluster is going to need about 1,000 wells. And the point about this is that this is a very realistic objective. It is very doable, and it's much, much smaller than the historic petroleum industry. And to show you, there are emerging projects, particularly in the North Sea Basin where I work, both on the UK side and the Norwegian side. There are many projects now trying to mature real storage. And I'm just going to show you this one example, which is also publicly available on the H21 Green website. It's the H21 program, which is a suite of projects to look at hydrogen deployment in the north of England. And the concept I was involved in was, what would it take to get 20 million tons of CO2 capture and storage by 2035? A very specific objective. And we concluded in that particular scoping study, it would take 12 subsea wells from 4 subsea templates into 3 geological structures. So, you know, I'm showing you this case to show you that this very ambitious, how many wells would it take to decarbonize the world, can be scaled down to very specific projects. And I think gives us some real hope that we can see significant CCS deployment in the decade to come. So let's wrap up, because I think I've taken too much of my time. The main findings from our offshore global resource assessment was that using the historical data, we could make an extrapolation to the future. And we concluded a single Gulf of Mexico well development could achieve all of the storage required globally. Of course, nobody's expecting the United States to do it. It's just a model. Alternatively, 5 Norways would do the same job, just as a dimension. But being more realistic, we think that cumulative storage that's needed by 2050 to achieve the 2-degree scenario is probably going to take 5, 7, maybe 10 regional clusters that are trying to store industrial captured CO2 in the offshore region. And they could also use the onshore. And the nice thing about this global study is that these resources, they are not owned by any particular one country. They are well distributed around the world. Each continent has good storage basins close to the main locations of capture. And our main conclusion is only going to take a fraction of the historic worldwide offshore petroleum well development rate to achieve the global storage requirement needed to meet the 2-degree scenario for global warming, which the world's nations have agreed upon in the Paris Agreement. I think that's a really nice, scenario. We can do this, and I'd like to emphasize, just to conclude, that this storage under the 2-degree scenario is only 13% of the CO2 reduction. That's 13%. Most of that decarbonization is happening by renewable energy and energy efficiency. Okay, this is only the CCS part of the global problem. So I really think I should stop there, Hadi and Sebastian, and I'm happy to respond to questions.
Well, thank you very much, Philip, for the very inspiring talk. I'd like to give the stage to Sebastian to actually start showing the questions and then having your remarks and feedback on them.
Thank you very much, Phil, for this excellent talk. There are plenty of comments coming through fast and furious. Lots of people thanking you for excellent, inspiring presentation, and try to group some of the questions. So the first questions that came through were from George Hutman and Andrew Moore, and they're related. They asked about the Northern Lights project, where you use ships to ship the CO2 from onshore to offshore. So how does that affect the CO2 budget, considering that the shipping industry is a huge emitter of CO2? How much CO2 can a ship transport compared to the amount of CO2 that it will emit during its journey? Or similarly, has a life cycle analysis for the shipping transport been done for the Northern Lights project?
Yes, it has. And I don't have the numbers to hand to give you a really precise answer. So I'm going to give you a conceptual answer. But what the project did is they said we could do the CO2 transport with future green ships that ran on hydrogen or renewable energy, but it's too expensive to do that. So they've gone for the greenest in class option. The idea is to try and run the ships on LNG rather than diesel. But they've done the life cycle analysis for a diesel ship as well as an LNG ship. And the philosophy in the Norwegian project is also to use the Northern Lights project as a stimulus to shipping developments, because we also need to see, as the questionnaire correctly points out, we need to see a replacement of diesel power for shipping. So the answer is the energy and CO2 penalty from the shipping is quite small if we use best in the class LNG shipping. But I don't have the precise numbers for you.
Okay, thank you. The next cluster of questions is all about seismic monitoring. So we start with Doma's question. I'm just going to read through the question. So seismic monitoring is essential in CO2 storage. Do future CO2 storage plans include the pricing of seismic monitoring? And related to that question, if I find it, is from Luke Jenkins, who asked the timescales of post-injection migration trapping are much longer than the duration of injection. For how long and how regularly will CCS sites be monitored after CO2 injection is turned off? So keep those two questions, and then I'll follow up with another one around monitoring.
Can I ask those two first? Answer those two first? Yes. Those are really good questions. How could I summarize? I think what we've learned, I said that the Sleipner project has collected 9 time-lapse surveys, and we're trying to reduce that for future projects to maybe 4 or 5 surveys in the lifetime of the project. So that's one way we will save money. And we published one paper on the costs, and using the Norwegian cases, we think the lifetime monitoring cost is about €2 per ton of CO2. And that includes the time-lapse seismic surveys. So time-lapse surveys are expensive, but when you scale it to the total operation of the project, it's really quite cheap. So that's my guideline number, is that roughly speaking, monitoring is going to cost you $2 per ton, €2 per ton. Obviously, every project is going to try and optimize that number, but we need to have enough monitoring to make sure we have a safe operation. So there's a balance between spending money on monitoring and saving it by not doing monitoring, because you might encounter new costs. With respect to post-closure monitoring, there's very few sites that have gone that far. There's one onshore site in Germany, the Ketzin pilot site, which has gone to post-closure phase. But I would say the general picture now is we're going to need at least one survey at the end of the project, just to confirm the CO2 is where it is. And then in the post-closure period, we would hopefully not need further surveys, but there would be the possibility to have them if need be. And certainly the Norwegian project, the Northern Lights project, is still discussing with the authorities, the operators are discussing with the authorities, what is the requirement for the post-closure period. And nobody's really resolved that yet.
Thank you. So, and then continuing with the monitoring theme, Gonzalo Zambrano asked, how accurate is the seismic monitoring technology to inventory the volume of injected CO2? How does the time-lapse seismic impedance, how is time-lapse seismic impedance correlated to CO2 saturations or concentrations?
Right. Now, I'm going to be pulled up by a geophysicist here, because I'm not a time-lapse geophysicist, but I'll tell you what I know from the published papers on this, is that the very best we can argue for Sleipner, in the top layer, we can probably detect down to 1 or 2 meters thickness of plume, certainly not less than that. In more realistic projects and deeper projects like Snøhvit, we're talking about 5 meters minimum, okay? So time-lapse seismic is never going to be able to detect every molecule of CO2. But if it can show the overall coverage of the plume, let's say it can detect 80% of the plume, and you use physics, like your understanding of plume dynamics to forecast the remaining 20%, which you can't see, I think that's a credible way forward. But I wouldn't like to leave anyone with the impression that you can see everything on time-lapse seismic. It's really just that with CO2 injection projects, you don't usually have many wells to monitor the CO2, so we are using remote geophysics much more than we would in, for example, an oil field development.
Thank you. Just the next question up again, talking about related in the broader sense monitoring. Pedro Mazzari asks, in 2013, a paper was published in Nature, starts out with seabed scars race, and they claim that CO2 started to leak at Sleipner. After 7 years, is there any evidence of leaking or non-leaking behavior at the Sleipner site?
Yeah, that's a good question, and there's a lot of interest in that observation. But our group in Equinor actually looked at the claim and looked at the shallow seismic. The seabed scar in that Nature correspondence, it wasn't a paper, was 25 kilometers north of the site and was related to a glacial channel, which we could see on seismic. And the seabed scar went down to, we think, 100 meters depth and was probably related to differential compaction in this glacial channel. And furthermore, we now know that the seabed scar was bubbling out biogenic methane. So there's no evidence for leakage at Sleipner, but the discussion around that feature, which we call the Huygens fracture, certainly led to a lot of speculation about leakage, but there wasn't any.
Okay, thank you. Another question around monitoring. Fahad Kamyabi asked, have you observed any supercritical CO2 in your CCS projects, and can you monitor the different phases? And how can you detect, using, for example, simulation, how long CO2 remains trapped?
Yeah, I mean, on the detection part, I think liquid phase and supercritical phase CO2 are not easy to differentiate from time-lapse seismic. What we can see on time-lapse seismic is the contrast between CO2 and brine. That's what gives you the very strong detection. if CO2 was to migrate from a deeper structure up to shallower layers, it would eventually turn into the gas phase, and the seismic response for the gas phase could be significantly different. So there are interesting studies on how good would you be at detecting shallow gas. So that was on the detection part. Sorry, what was the second part of the question?
It was around the trapping. For how long is CO2 being trapped?
Yeah, and that's definitely an area for continuing research, because what we can show at Sleipner is that we can see the mobile phase of the CO2 up to a certain resolution, but it's very hard to know how much CO2 has gone into the dissolved phase. But interesting enough, the gravity survey data, there's been 2 really nice papers on that, which have shown that we can at least put an upper limit on the amount of CO2 that's gone into the dissolved phase, because the CO2 dissolved in brine becomes a little bit denser. So you can actually use gravity inversion to try and work out how much CO2 has gone into the brine phase. But we can't pin that number down very accurately. So I think in the future, we're going to need more work on how much CO2 ends up in the dissolved phase, the brine, or potentially into mineral phases. And they are currently hard to pin down.
So continuing now a little bit with the plume migration or the CO2 migration, Guillermo Facchi asked, have you included any temperature dependencies in your model to account for thermal effects that might affect injectivity and plume migration?
Yes, I mean, the answer has to be yes. I mean, I tried to say at the beginning in the discussion of the phase diagram that the thermal effects are really quite important. In a lot of the early modeling studies, they were isothermal without any thermal coupling. But more and more, as we look at this problem, we realize that you do need a thermal simulator to handle this problem. And I showed you some examples from the Williams and Chadwick paper on the Sleipner plume, and they looked at those thermal effects in quite a lot of detail. So you could maybe look at that to follow up. But I think what's happening in the, if you like, reservoir simulation domain for CO2 storage projects is that an increasing realization that you do need to take into account thermal gradients in your simulation. And another thing I reminded to say is that the temperature change you get, if you inject cool CO2 into a hot formation, you can also get thermal fractures or some rock mechanical effects. So to some extent, there's a suspicion that thermal fracturing near the well could be an important process that we need to understand better.
So we move now to quite a series of questions to talk about economics and investment decisions. I start off with a question from Kate Hadi. Do you think that the possibility of encountering geological surprises as a result of an initially sparse data coverage will discourage investment in CCS projects?
Obviously, I hope not, but I think one of the reasons why I want to emphasize it, I do not want investors to think that you just drill a well and inject the CO2 and it'll all go fine. To make a successful CO2 storage project, first of all, you have to have good engineering design, and secondly, you have to have an ability to respond to operational changes. But the operational surprises that I showed you about at Sleipner and Snøhvit, for example, none of them stopped the project. They just caused a temporary halt, and then a solution was found. So I think it's very important to have that discussion between investors in these projects and operators, because certainly in the early phases, I think a lot of the investment is going to come from governments who want to stimulate the green transition. And it's important that the investor group appreciate the engineering design part. There are lots of analogies out there, but when you buy a car, you've got to drive it safely. The person that sells the car isn't going to guarantee that it will never crash. You have to drive it carefully. And so I think the argument I would make to an investor for a new CO2 storage project is that it's a very good investment. You're injecting a large amount of CO2 in a few wells, but you have to operate those wells in a careful, diligent manner. I don't know if you are aware of the fact, but the Sleipner injection well disposes of the CO2 per year equivalent to 1/10 of Norwegian road traffic. So, you know, it's a very significant benefit in terms of, you know, climate action. So as long as that one well performs well, it's a really good investment. But no doubt that question is going to be a hot topic for the years to come.
So related to that investment decision, Pat Corbett asked, the oil industry has recently promised a green capex. How serious do you think is this commitment?
Yeah, that's a hard one to answer. What I have personally experienced in the last 5 years, you could say, is 5 years ago, carbon capture and storage was a very peripheral activity, which you could say that a lot of large energy companies were not taking very seriously. But in the last 2 or 3 years, it has totally changed. The interest in significant CCS investment, you know, in 2019, 2018, is really quite different. So I would hope that the gestures we're hearing from the business leaders is genuine, and I can see a lot of evidence that it is.
Okay, sorry, there's so many questions. I'm just trying to group them into themes. There are a lot more questions around efficiency and economics. So I'm just going to try and pick out two that are slightly related. One is from Lee Meng, and who asks, the most expensive part is CO2 capture. What are the common techniques that can reduce cost? And then going to the storage side, Mohamed Ali asks, do you think there's an opportunity to enhance the storage efficiency beyond the 6% from fundamental operational point of view?
Yeah, great questions. Yeah, roughly speaking, I mean, the capture part is the most expensive part of a CCS project. You know, as a guideline, it's about 80% of the cost. You know, obviously it varies per project, but it is the most expensive part. But we have seen in the capture technology, you know, incremental but significant reductions in cost and improvements in efficiency. The Boundary Dam project in Canada, they published a study claiming that they could probably get a 60% improvement in cost. So I think there is good potential for reducing the cost of capture, but no magic bullet. I mean, I think we're going to see incremental changes there. The second part of the question was about the, sorry, I've forgotten. The second part of the question was about?
So the second part of the question was about the increasing the efficiency for storage beyond the 6%.
Thank you. Yeah. No, I think there's a lot of potential for that. And, you know, what we've been trying to look at is saying, okay, if the physics, if you take a homogeneous sand and the physics says 6% is your maximum efficiency, could we use the geology to our benefit? Could we understand the distribution of layers and baffles to improve the efficiency? That's one way we could do it. And in the Sleipner case, the 9 layers that we observed with shale baffles definitely did improve the efficiency with respect to a purely homogeneous sand. And then the other thing you can do is play around with the physics a bit. And you could say, well, is there a way we could disperse the plume near the well to get more access to the pore space? So I think there's a lot of potential for improving the efficiency. And of course, the other thing I shouldn't forget to say is that if you do fill a structure with CO2, then the efficiency is significantly higher than 6%. I mean, you can imagine a structural closure could have 50 or 60% CO2 saturation, but only in that closure. Whereas the numbers I was talking were about the whole storage domain. So a lot of potential, yes.
You talked about the analogy of driving your car safely and operating your well safely. So there, again, a set of really interesting questions around operating your wells and the being sure that you're not exceeding fracture pressure. So I'm trying to pick a few ones here. So the three related ones. So the one is from Neil Price. What is the benefit of a horizontal injector versus vertical injector? And let you answer this while I pull out the next set of questions.
Okay. Let me answer that one first. You know, I also sort of started with a lot of enthusiasm about horizontal wells, because you could, with a horizontal well, access a lot of reservoir and improve your injectivity. So I think down the road, horizontal wells for CO2 injection will be good. But what we've learned about is that in the early projects, you might prefer the flexibility to be able to access different horizons. So in the Snøhvit case, the fact that we had a near vertical injector with multiple completion intervals added a lot of operational benefit. But if you are very confident about your storage unit for, say, the second or third well, then maybe you'd start to go to deviated wells as a solution. So yeah, it's a bit of both, but definitely horizontal wells could be very valuable. And they were, in fact, tried in the Insala project, or successfully used in the Insala project.
Excellent, thank you. So continuing around the well theme and the safe operations, Helen Lewis asked, is fracture pressure really the right upper limit? If a rock is already fractured, as almost all are, the upper limit will be considerably lower. And then related to that question is one from David Latin. Asks, how much do you worry about the state of stress and faults and the ability of small pressure increase to move things?
Yeah, these are smart questions. So one of the biggest uncertainties we've found in planning new projects is knowing the stress field in sufficient detail to estimate the fracture pressure is a major uncertainty. So we've often tried to argue you need extended leak-off tests, for example, that will give you a better estimate of the minimum fracture pressure than you would get from just standard leak-off tests. And it's also very true that there's several fracture pressures to worry about. There's the fracture pressure of the sealing unit. There's the fracture pressure of the reservoir before injection. And then there's maybe some dynamic of how the fracture pressure evolves if you've got natural fractures versus hydraulically stimulated fractures. So yeah, in reality, it's a complex story, and no doubt natural fractures may be quite important in assisting storage, right? You might want some natural fractures to give you beneficial storage, but you will need to convince the authorities or whoever you get the license from for a CO2 storage project that you definitely haven't exceeded the fracture pressure of, say, the cap rock.
Thank you. So Hadi, as indicated, we have about 2 minutes left for questions. I'm going to pick 3 questions that are related to your forward look of how we can scale up CCS. And again, so they're quite related to each other. So Nathaniel Inskip asked, is it possible to reach the necessary amount of projects required to meet Paris targets based on the current carbon price? If not, what would the price need to be? And related to this, Philippe Doma asked, can we reach the Paris goals with existing reservoirs, existing wells, with some local extra drilling, or do we need to find extra wells? So what are the costs?
Yeah, we definitely need more wells. There's no doubt about that. But I tried to argue that it's a realistically number of wells. About the carbon price, I mean, yes, I think the carbon price would have to be well above, say, 50 euros or dollars to start really pushing this technology. The ETS has, I think, recently risen up to about 27. In Norway, the carbon price is just over 50 euros. And the Sleipner project, you know, is a business proposition because of that, you know. So I think my picture would be the carbon price would need to be significantly above $50 to start really accelerating this activity. But the other thing is that there needs to be a willingness to decarbonize. What I've noticed is that in countries that really do want to see their emissions reduced, they quickly come to the conclusion, or maybe slowly come to the conclusion, that you cannot do it with only renewable energy. You need to find a way of decarbonizing your existing industrial infrastructure. And so there has to be some political motivation. I don't think it's just the carbon price. I think there has to be a social willingness to decarbonize our societies. And when that social willingness is there, then I would say, the technical solutions are ready to deliver.
So there are plenty of additional questions, and I apologize to everyone whose questions I can't ask. No, fantastic question. I think we could easily discuss it for another hour or so,
right,
talking about mineral trapping, costs, etc. I'm just going to pull up one quote, and I think that speaks from everyone. Was from Royal Geologist, fantastic presentation, best one I've seen on the topic, and first one showing quite a bit of subsurface data. Well done. So Phil, thank you very much from everyone, from me on behalf of everyone, for a great talk, and apologies to everyone whose questions I couldn't read due to the lack of time. Hand over to Hadi for some final words.
Yeah, absolutely. Thanks, everyone. Hard to cut this very energetic discussion. I would like to just announce that our next speaker of next week would be Mark Zoback from Stanford University. Mark will speak about induced seismicity and reservoir geomechanics. So stay tuned for the announcement of the link. Have a nice week ahead, and stay healthy, safe, and happy. Until next week. Phil, thanks again one more time.
Thank you for organizing. It was a great chance to be here.
Pleasure.
Thank you.